Okay, here we go. Hall effect. Um, so this is the only time where Ben Franklin's positive charge flowing in the direction of current falls apart that I've come across. Okay, so you have to be a realist, meaning you have to think of which way the electrons are flowing. Okay, um, so so we're going to say current flows to the right through a conductor that is in an external magnetic field directed out of the page. That's this guy. Okay. Which way are electrons forced? Which way are electrons forced? So you have to be a realist, and you have to think which way electrons are flowing. Tell your neighbor. Correct answer is so electrons are going in the opposite direction of current. Electrons are negatively charged down. Yes? Electrons are going in the opposite direction of current. So your thumb goes to the left. Electrons are negatively charged. You're right. Okay. Electrons are going this way, yes? Okay. They're negatively charged. Back of the hand. Because this, doing it, okay, Ben Franklin, you get positives going down. Yes? That's not the right answer. The right answer is you have to take into account both the fact that it is going, electrons are going to the left in the opposite direction of current and that they are negative. It's not a double negative. It's like you have to incorporate both of them.
When will we know it's this?
Hall effect.
But,
It's the only time.
but like when will we know it's this?
It'll say Hall effect.
It will say specifically Hall effect.
Hall effect. Okay.
That's so lame.
Okay. Good with that. So that becomes positive. Polarized. Yes? Okay. So what is the direction of the electric field due to that polarization of the charges? Tell your neighbor. Correct answer is down. Out of positive into negative. Yes? Okay. All right. Um, so a lot of times, quick disclaimer here. They will say, if they say on the AP test, you have the Hall effect and the charge carriers are positive, then you can do Ben Franklin. Okay. But the reality is they're negatively charged. Like if you go out in the industry, you have to deal with this. Like it's not positive charge carriers, they're negative. Okay. Um, so what this causes is there's an electric potential difference across this conductor. You're right with that because of that polarization. Okay. Yes. Okay. And it's going to polarize until the electric force is equal to the magnetic force. Like it'll continue to shift until these two forces, the force from the electric force from the field developed, cancels out the force of the magnetic force. Charlie.
What's causing this particular effect?
You have current running through this conductor that's in a magnetic field.
So it's just true for any.
Yep.
Okay, so like a wire that's been extended.
Okay. I don't want you to apply it to those scenarios because rarely do I ever care about what's the voltage across a wire. Usually it's going to be a slab of conductor. Does that make sense? Okay, like I need this. I don't want this to be a stumbling block for you. Like, oh, I've got current through a wire. Like, yes, that this does take place. However, the voltage across a wire is so infinitesimal because it's going across the width of the wire, which is who cares? Okay, it's when they give you a slab, they'll give you a block. That's how you know, oh, I'm dealing with the Hall effect. And then they will probably tell you, hey, it's positive charge carriers because everybody's going to be tripped up the fact that they can't do Ben Franklin like a conventionalist. Okay, but in reality, it's a negative and it falls apart. Ben Franklin falls apart on this one. Okay. So this is showing which way the electrons are going. Electrons are going to the left. Tell your neighbor.
Yes. I thought it was like a ground wire. Like,
Correct answer is bottom. Okay. Electrons are being forced up. So this has a lower electric potential than this. This has a higher electric potential. Good? Okay. So this gets kind of into the math part. I would not write this down. This is you. If they give this to you, it's going to be a free response question, multiple parts. You're kind of going through these questions here. You're like, hey, which one has a higher electric, like which way is electric field going, which way is the electric potential, and then they say, okay, all right, so you've got a conductor, thickness T, width W, has electric field. So the voltage across this. So this is looking at positively charged carrier or positive charge carriers. There's a electric field across this. There's a distance. Where did that go? There it is. Okay, this is just this equation. If the electric field is constant, it's electric field times distance. Okay, that's what we're doing right here. The distance would be the width. Josiah, question? Yes, I can. So you're holding your hand like this. This is the direction of the electrons. Field's going in. Electrons are being forced up. So this has a lower electric potential. So this has a higher electric potential. Okay, electrons are being forced or moving to the left. Field going in. Electrons are forced up. Good? Okay. So here we're looking at this. This is more or less the math part of things. Okay. So you've got this electric potential, electric field, and the distance. In this case, it would be this distance here. We have electric field going down. This would be the distance to find the electric field using this equation. Okay. Once it reaches steady state, we have the forces equal to each other. So we know that the electric force is charge times electric field. You're looking at electrons, and this is the magnetic field times the charge times the velocity perpendicular. Okay, charges go away. Okay. But we don't want the charges to go away. We want the electric field. Oh yeah, no. Why did they not take away that? That is a true statement, but I don't want to do that. Velocity. What happened to my velocity? Oh, there. Ooh, yuck. Okay. So drift velocity. Oh goodness, yeah. Okay, so this is like way back the microscopic view of current. Okay. So current is equal to the drift velocity times the area, which is this, times the N is the number density, yes, and over, what is that over? It's per length, I think. Per volume, I could be, yes, I could be convinced with the volume. What is that? And then times the charge. Is that right? Volume times the charge. I want meters. Okay, so that's, yeah, I think you're right. So that's meters per second. That's meters squared. This is just a counter per meters cubed. Yes, I like it. And that's coulombs. So I get coulombs per second, which is an amp. Whew. Okay. So we used that there, and then that substituted that out, and we get that. Charge carrier density. Charge meters. Look at that. Okay. So, Hall effect.
Well, we need to like derive that equation.
Maybe.
Oh.
It's in the realm of possibilities. Okay. Yeah, I know. I saw that too. I'm like, yeah. Oh, I see what they did here. They just did this. They substituted that in for that. That's what they did. And then they put all that junk into here. That's where they got that from. Okay. Good. Solid as a rock, right? Clear as mud. You like mud? Tell your neighbor.
Sure. Like we're gonna create a black hole and it's just gonna fall point to the side. Press it. The electrons are going to off the back of the gas above the play back into the negative side. Which points feel about. So is it when it has the like the voltage change thing for like a battery or like EMF or whatever? Is like the longer one representing
Yes.
Is that why it's the longer one?
I don't know why they picked it. It might be. I remember it short, negative, long, positive. That's how I remember it. That's just okay. Is everybody good with up? Okay. The electrons are going out of negative into positive. Because current goes out of positive into negative. So electrons are going this way. I want the electrons to be shoved back. Because I want this to be positive. Fingers are going up. Good? Okay. Hall effect. All right. Magnetic force on a wire. We've got A magnetic force on a charged particle, that's given to us. Okay. This is, don't worry, don't copy this down. This is magnetic force on a chunk, a group of charges moving at some drift velocity. You're out of that? Not too bad. Okay. So I want to express this rather than a chunk as current, because current's the chunk of charge flowing at a certain per second. The drift velocity is that length divided by how long that took to do that. I don't want to deal with time. That'd be really nice if I could get rid of that. So I shove in charge is this. Drift velocity is that. Time goes away. So nice. And I'm left with, here's how I remember this. Magnetic force on a wire is equal to Bill. Okay? This is the equation they give you on, this is the equation they give you on the equation sheet. Okay? If the, it's just magnetic field times the length that's perpendicular, or like, you could either look at the current or the length that's perpendicular to magnetic field. Okay? Good with that? Okay? Did everybody understand this fictitious diagram? This line is just the boundary line. There's nothing physically there. Tell your neighbor. D-winged bubber. Correct answer is D. Dangerous dinosaurs. Good? Okay. Your current's going to the right. Magnetic field's coming out of the page. Down. Okay. Here, the current's going up, being forced that way. Here, the current's going down, forced that way. These two forces cancel each other out. Net force down. Yeah? Okay. Huh? What? What is the direction of net force? Yes. What is the magnitude of net force on? Oh, magnitude. Got it. Gave that away. That was stupid. Tell your neighbor. Bill, Bill, Bill. Okay, these two cancel out. What? Do what? Sort of, not really though. The Ampere's law was this is zero because the magnetic field was going perpendicular. That was like looking at the field created. This is like the force.
Fully into
Uh,
what we want.
okay, here comes a this conversation would be helpful for a free response problem. Okay, a long vertical wire current with current I's flowing up through it. A rectangular loop of wire 2L plus times 5L is lying parallel the vertical wire and is in the same plane as the wire. Magnetic flux is just like electric flux. Magnetic field times the area is specifically phi, phi, fo, fum. B is equal to the integral of magnetic field with area. So what is the direction of the magnetic flux through that? This is always going to be in the same direction as the magnetic field, which would be, here we good with, out of the page. Okay. What is the magnitude of the magnetic field created by the current in the wire at a distance r away from the vertical wire? Give you a chance to think about that. I want to know how strong the field is right there, that distance away. Okay, you're doing Ampere's law. Okay, that's our Amperian loop. So we've got magnetic field times dl, which integrating that is just b times 2 pi r. Yes. Enclosed is just current. Oops. Nope. There's nothing in the fraction there yet. Equal to mu naught I. So that is just equal to mu naught I over 2 pi r. Boom. Okay. Simplest form of a magnetic field using Ampere's law. Okay. What should you substitute for dA so that you can evaluate an integral in terms of r? This is way smaller steps than they would give you on a free response problem. I'm just kind of walking you through a baby step. I'm looking for dA, but I want the area, a little sliver of area. That gives me something in terms of r that I can integrate, specifically dr. I would do 5L dr. I want this. I want the area of that rectangle. That's going to be a little dr. Length times width, yes? dA would be equal to 5L times dr. Yes? How we doing? Okay. So I want to find the flux. So this is where I need some space. So flux, magnetic flux is magnetic field times dA. So area is 5L times dr. I'm going to integrate this from what to what? I'm going to go from L to 3L. Yes? Okay. And Oh dear. I'm not writing this very. My grader would not like me. And I'd lose points because I'm not being organized.
Oh, you have to write the pi equals every time.
You know what?
Yes, that's absurd.
Okay, well, just telling you how to make your graders happy. You want your graders happy.
Should we write compliments?
No, kissing up. Kissing up would not help your cause. You're doing great. Thanks for grading me. We appreciate. No, don't. Aren't you glad I got this right? You didn't. All right. So you'll make your graders happy when you get it right because then it's a quick. They have a quota. Okay, if you get it right, you're like, oh, I like this kid. But they only grade one question, just a whole bunch of times. Yeah, you got to be consistent. And then then they give it to another team, and they grade it. So your score is not just based upon one person's opinion. Never. Never. Some people like it. Like it's like a thing. They're like, yeah, it's a party. I hate I hate grading. You guys know how long it takes me to get my quota. I would totally break like yeah, they're like Smiley, what are you doing? Get out of here. All right. So do we understand what we're doing here? Okay. So I'm going to pull out everything that's constant. And I just have 1 over R. dr. L. 3L. So I get natural log of 3L over L. Yes? So natural log of 3. Boom. Okay. Hey, we did it. Look at that.
Was you simplify I to 1, E to 1, 3 to 1, then you can make a bunch of that go away.
Okay.
Small everything approximation.
All right. So
I had 2 good balls, so I didn't small everything. Small perpetuity of free space.
okay. We're given some numbers. So let's say the current's 10 amps and one current. Ooh. Oh. Okay. 10 amps in this one. 1 amp in this one. L is 10 centimeters. Evaluate the net force on the rectangular loop of the wire from the vertical wire. Okay. So, I'm going to get rid of most of this. So I don't need it. What I'm looking for, need that. I don't need any of that. That'll come later. I need that. Okay. And so I've got, which way is it going? Clockwise? Flowing clockwise. Nope, that's counter. Okay. So here the field's doing this. Yes, getting weaker. That was a quick quick weaker. But anyway, good with that. It's getting weaker. So here we're going out of the page down. This guy's being forced this way. This guy's going to be forced up. This guy's being forced down. This guy's going to be forced that way. Is the net is the net force 0? No. Which way is the net force? To the left. Because the field is stronger here. So I'm going to find the force. Nope. I'm going to find the field. And then I'm going to do Bill. Which is perpendicular. Okay. So I'm going to do it on the right wire. So that's 10 amps. No. Yeah, it is. Sorry, let me do this. Let me do this in a different color. Okay, this is B. So that's 10 amps over 2 pi times L times 1 amp times 50 centimeters. Yes? 5L. Okay. And then I'm going to do the same thing for the left side, except this is going to be 3L. Sorry, that should be 10 centimeters, so 0.1. Good with that? Okay. What is the net on the vertical wire from the right? Ooh. Okay. So these two cancel each other out. Okay. But what happens if they say, what's the force just on the top of wire? Oh. Oh, shoot. Magnetic field isn't constant anymore. Dogs.
Does it have like just like the wire have like thickness?
We're going to say infinitesimally thick. Sorry, infinitesimally thin. Infinitesimally thin, not thick. Okay, so we're going to look at how are we doing with that? A little length. Okay, so we're going to integrate that. This is going to be this. You have that? This is just 1 amp, and then DL is just going to be a little change in DR. You all right with that? All right, integrate that from L to 3L. James.
Why is there even a force to it? Because when thickness just be 0?
The thickness of what?
Because we're doing the top part of the wire, right?
Sorry, we're looking at this part of the loop.
Yeah.
If
there's no thickness to the wire, then there's no perpendicular section of the length.
Sorry, what is the magnetic force on the vertical wire?
Oh, the magnetic field.
Oh, oops, sorry. What is the magnetic force on the vertical wire from the rectangular loop? Oh, I'm sorry, I'm not answering the right answer. Whatever I get here, that's that answer. Newton's third law.
Okay.
Sorry.
I thought you were like setting us up for like they give us a trapezoid or something.
What I was doing was I was finding the force on just this part here.
They give us a trapezoid. They don't think it's loud. What's the acceleration?
Haven't seen it yet, but I could see that at some point. I haven't seen it yet on a free response yet.
This year, next year is not this year. You've never seen a trapezoid?
Okay.
Bless you.
Did I sign this? Maybe.
Let's do it now together anyways. Yeah.
All right. Section of a long cylinder, conducting cylinder with inner radius A, outer radius B, carries current that has a uniform current density. Oh, we like that. Uniform current density. Ampere's law for an expression of the magnitude of magnetic field in the following regions as a function of distance r from the central axis. So less than A, so that would be no enclosed current. Yes? Okay. 0. How about in between there? So that would be in here. So now we got to do some math. This is, well, not as easy as we thought. Yes, that is easy. That's easy. That's just I naught, mu naught, I naught, 2 pi 2b. Yes? Good as that? Okay. That's for everything. We have that. We know that that's a known current. So to do the green, we know it has a uniform current density. So that is current over the area. You could do pi b squared minus pi a squared. Yeah? Good with that? And then we want to do I want to integrate this, or can I just do a ratio here? think I can do a ratio. So current in is equal to pi r squared minus pi a squared, yes? Because it has a uniform current density. So I can just straight up do that. And so my current in is going to be pi r squared minus pi a squared I naught over pi b squared minus pi a squared. So you stick all that. Ugh. You could get rid of the pi's. So you would have mu naught r squared minus a squared over b squared minus a squared I naught over 2 pi r. Boom. Yes? Okay. On the cross-sectional area diagram, indicate the direction of the field at point P. Current's going in. That's going that tangent to the circular path. Easy peasy. Electron is at rest at point P. Describe any electromagnetic forces acting on the current. Justify your answer. An electron is at rest at point P. We would say no force because it is at rest. Even if, okay, so check this out. Here's point P. Let's say you shot it that way. Nope, not that way. Let's say you shot it that way. No force. It's going in the same direction or parallel to the direction of the magnetic field. And is that it for that 2000? Ooh, gross. Now consider a long solid. A solid. Okay, so we're solid magnetic field inside the cylinder. Function. Okay, we did this. Go cramp. There it is. We did this already. Okay. And they gave us it. Yes. That's the equation inside. Whew. Draw a straight line. Use the slope to estimate the permeability constant. So, yeah, that's easy, right? They gave us this. They want us to solve for that, so we just do this over that. They gave us this. So we find the slope with this times 2 pi b squared over I. Yeah? Look at that. Done. 15 out of 15, 2011.
If we do that right there,
Like, I mean, we just did. That was E&M number 3, 2011. Okay. All right. Boom.